All right, now we're rolling. Master set 4 or 5 concept due a week from today. And then the Thursday after spring break, the 4 or 5 application master set is due. Any questions? All right. One last problem I want to do of the straightforward kind before we start getting into the circular motion. The book and the coffee cup. And we'll make mass of this object right here. Sure, it's massive. And this will make kilograms. This angle. Initial speed is up the ramp. And make it 10 meters per second. And x is distance book travels before stopping. And what I want to know is, what is x? Let's see, need to give a little bit more information because there is friction involved. Use of S, 0.4, use of K, 0.3. And ideal pulley and rope. Now, if that's a book, that's an incredibly massive book, unrealistic, but I call it the book and the cup problem because it comes from a textbook problem in which it was a book and a cup. All right, so first step. What's the first thing we do?
Force diagram.
Absolutely. That would draw slightly better. And then we assume that there is ground underneath here. It is not a bottomless pit. All right, so doing force diagrams, so we got our checklist here, F tone. All right, what?
Tension on both ends of the rope.
All right. So tension pulls.
Yep. Yep.
Now what?
Normal force on the, is that the, yeah, that's,
The book,
yeah, on the book.
box, whatever it is.
And it's perpendicular with the,
And so go in that direction. Like that.
yes. Should be facing towards the surface,
So the normal force on the book is this way?
correct, I think.
That is normal
Up
force.
on the surface,
Pardon?
and then up on the surface,
So, like that.
yes.
Yeah, there we go. Normal force is a pushing force. So the surface is pushing the book that way. I guess why is the B? Why is the B? There's another pair of normal forces out there.
On the pulling of the rope.
Yes. And so it's what causes the rope to bend here. So we have this normal force, R. Why is it R? Okay. That's it for normal force. Can we eliminate anything?
Okay.
All right.
We have friction.
Acting which way on what?
The first box, or book, what, yeah. So it wants to go down the ramp, so opposite of. It wants to go up the ramp.
The book starts out the problem already
Oh.
moving.
Okay, so friction going down the ramp
Yep.
on the book.
And then other way on the
Yes.
ramp itself, okay? If the book started out at rest, then the first thing you said is absolutely right, but I am throwing that the book is moving to start with.
I just ignored that.
Its feelings are not hurt. So friction between any two other objects?
You say that is the ideal pulling rope, so that,
That's it. Normal force is required for there to be friction, and I have only two pairs of normal forces. I have this pair and that pair. This, no friction because of ideal nature, and that we just did. So friction done. Saving the easiest for last, okay. I guess I consider it the easiest. Bueller? All right,
wait,
is there any weight?
yes.
I hope so. Which way is it acting?
On that ramp.
Towards each other.
So on the
No,
box
no.
towards the ramp, and from the ramp towards the box.
Right, so like that?
Yes,
Yes.
yes,
Keep going,
okay.
keep going. There you go.
Weight is always acting on the smaller object, always down.
Okay.
Weight on box, and then weight on box.
And the other one's cut.
All right. Weight on cup. Weight on cup. What we really care about, why the force is acting there, the rest of it was just sort of practice. But I care about the cup and the book. All right, so what's next?
Acceleration direction.
All right, so which way is the book accelerating?
Going up the ramp.
It is going up the ramp.
Right.
Oh, you're saying the acceleration's up the ramp? Greg, you're changing your mind?
No, I just said the acceleration is going up the ramp.
Okay. You agree? So if this book is going up the ramp and the acceleration is up the ramp, what's the book gonna do?
Go faster up there.
Yes. Is the book gonna go faster as it goes up the ramp? Not under ordinary circumstances. There have to be some other force involved there. So, also from a force point of view, there are no forces acting up the ramp. So there's no way that the book can accelerate up the ramp. So acceleration is the other way. And what about the cup?
Down as well.
I heard down and then I missed it. So it's moving opposite direction of acceleration. Thus, as mentioned or implied earlier, it's slowing down. So now we do our coordinate system. And so this is the point. I've made references earlier that you generally have one in the direction of acceleration, and then the other is perpendicular to it. But not always. There's a case right here of, do we want to make the direction, one of our coordinate system axes, in the direction of movement or the direction of acceleration? They're in opposite directions. So if we make the acceleration this way, or sorry, if we make our, I'll just say I hat in this direction, then I expect a positive acceleration. If we make I hat in that direction, I expect a negative acceleration. It doesn't matter, but we do need to be consistent. So, I hat up the ramp or down the ramp? I saw an opinion for up the ramp, so we will set it that way. I hat. And then J hat's perpendicular, which means, you know, in a two-dimensional problem, it's either that way or that way. And it really doesn't matter, just you pick one. Good. Okay, I saw some hand gestures this way. And then down here, it's a one-dimensional problem for this one. And since we said up the ramp was positive, that will make up positive here so that they are both moving in the positive direction to start the problem. Now you could get away with just writing a plus sign here, but we'll just write I2 hat. Or I sub C, just to be consistent with my subscripts. All right, so we got our coordinate axes now. We've gotten, let's see how far we've gotten. We did our force diagram, acceleration, coordinate axes. All right. What's next?
Decomposition.
All right. Do we have to decompose anything? Do we have to break any vector up into its components?
Yes.
What do we have to break up?
Weight on the box.
All right. It is the only one that is not parallel or anti-parallel to my coordinate axes here. And then down here, they're both vertical. My system is vertical. We have done this enough. I'm just going to call that theta, just so we can keep it in general terms to start with. And so my box now, I have friction acting down the ramp. I have tension acting down the ramp. I have normal force acting away from the ramp. And then weight, I got two parts to it. I have, squeeze it in here, W sine of theta down the ramp, W cosine of theta into the ramp. And then the cup is as the cup is. we don't do anything with that. Now what?
Equations.
How many equations are we gonna have? Which is the equations of motion. How many?
Four.
Why four?
Because you have your, wait, no. Never mind.
What's your gut telling you it's now?
Well, originally four, and then you have the one down there,
So you have the one down there and,
then you have that one and that one up there.
you said that one and that one, these two?
Yeah.
They're the same, they're the one and the same. The only difference is that the friction, the tension, and the normal force are already on. I just rewrote those. And instead of writing weight straight down, I broke it up into parts. So this would satisfy, this substitutes that. So how many equations from this one?
Wouldn't it just be the same thing as that? Wouldn't it just be the same thing as that one up there?
Is this one right here?
No, like, that one up there.
I'm not following here.
Oh, that one here.
That one?
No, that one,
The purple.
the purple one.
Purple. That's the coordinate system. So how many equations?
It's two.
Okay, that's two. How many down here?
Would it also be two, or one, since it doesn't have?
Yeah, ultimately it's gonna be one. You could, if you wanted to write a horizontal equation here, you'd end up with 0 equals 0, which is a true statement, but it doesn't really help much. Typically, so I have one here and I have two there. So 3 total.
Okay.
Right. My template is F equals MA. See if that one's still right. All right, so what are the three equations? So I guess we have our IB hat, our JB hat, and our IC hat. James, you looked like you were about to say something. Okay. Anyone?
For, JB hat, it's gonna be y minus the weight cosine theta equals 0. And if you're gonna take it a step further, it's just the two equal to each other.
We'll just leave it right here for now.
Okay.
We'll get to the next part in a second. All right, one down. Oh, I somehow lost my subscript there. Should be YB and WB. I'll wait you out. Get comfortable here. Yes.
So I'm doing the I hat B.
Okay.
Yeah. FT minus WB sine theta equals MA.
Alright, there are a couple things missing, but you gotta start it, appreciate that. You wanna take a shot at what you missed?
I'm looking to see.
See, the third force there. Friction.
So it'd be plus or minus FB,
Which way is it going?
in the direction with, in the same direction as the tension and,
Alright,
With minus, correct?
so minus FB?
I wanna say yes.
If. Oh, is that B?
We established up the ramp is positive, so anything going down the ramp would be in the negative direction. So
Correct.
these, all three of these are negative, so that explains one other thing missing.
Negative FT?
Yeah, they're all negatives. And another thing which you might correct, if you were doing this on a test, you might correct it when you actually start plugging numbers in, or you might not, it depends. There is, for completeness, there is one other thing missing. Craig sort of mentioned a key word just a moment ago.
I mentioned the keyword.
You misread it and then realized what it was. All right.
Alright.
B.
Yep. Dang it.
Because we do have two different masses here. Subscripts become important when you have more of the same, more of one type of thing. All right, so we got one equation to go. Well, I'm glad there was acknowledgement that there's one equation to go. I have confidence that there's more than one person in here who has a pretty decent idea of what it's supposed to be. All right. You look at the forces.
WC plus FT equals MA.
WC plus FT equals MA. Two issues,
Oh, and C.
one issue. No, there's no, the bottom cup down there, there's no angle involved really. Not directly at least. Think about the forces over there and the directions of forces.
is it a negative A minus A?
WC minus FT. MCA.
All right. The fact that there's a missing minus sign is true. The question is, where do you put it? Again, we established the coordinate system. We did the coordinate axes before we do the equations on purpose, because we need to, that tells us what's positive and negative. Over here, we had up is positive. Therefore, what is negative?
Negative.
WC.
Yeah. Somebody said that earlier and I missed it, I apologize. You don't put the negative next to the acceleration because we're expecting acceleration to be a negative number. All right, we got our equations. Now what?
Change weight to mass.
Substitution.
It is substitution, but I was waiting for Craig to finish up there. Because where he's left it, it's a huge no. All right, so substitution. So what are we substituting? For what do we have an independent formula that is true no matter what problem is? These are all problem specific.
Weight and friction, correct?
Okay. So what is the weight formula?
Mass times acceleration due to gravity.
Right. Craig, what I heard you say earlier is substitute mass for weight, and
Correct.
mass and
Times
weight, not the same
acceleration.
thing. Are we dealing with kinetic or static friction here?
We are kinetic.
Yes. And this is the nice advantage, at least for telling you it's already moving, is you don't, it's static is not involved. At least not until it stops. All right, so we have kinetic here. What's the formula for kinetic friction?
FK equals U minus K1.
All right, you get what? So if we do those substitutions here, we'll rewrite our equations except with these things in place. So I have negative ft minus mbg sine theta minus mu k y b is equal to mba. The first one. Second one, yb minus mbg cosine theta equals 0, and then negative mcg plus tension is equal to mca. And then the last step is actually solve. It's now a math problem. We're trying to solve for A. Typically, you plug in for Y, add the equations. And then skip, sing songs, celebrate. Or go on to the next problem. So I have negative ft equals, not equals, where that came from, minus mbg sine theta minus mu k mbg cosine theta equals mdA. And negative mcg plus ft is equal to mca. And MCA, just line it up a little bit better. And add. So what do we end up with in the end? How do you add? Alright, I'm just gonna get comfortable again.
Might as well.
I guess, hint, we've done this on previous problems, so you can always check those. While you're figuring out what I mean by add. Anyone ready to take a shot at this yet?
So your FTs cancel out,
Yes, they will.
so you're gonna be left with negative mg sine theta,
Indeed.
mb, sorry, sine theta minus mk, or mu sub k, mb cosine theta.
There's a G in there, but.
Yep, I'm sorry. Divided by M1 plus M, or MB plus MC equals A.
You left one thing off and you skipped a step, but, I
Okay.
mean, skipping this step can be done if you're